Okay, are there any questions from last time? So we sent out an assignment today. I have to apologize a little bit that the assignments are a little out of phase. The assignment is from some slightly older work. We should have sent it out some time back. So I'll quickly give you another assignment after this. Okay. Submit this next week, and then we'll have another assignment. So we'll try and catch up. Okay. Okay. Good. Are there any questions from last time? We discussed Feynman diagrams and so on. Basic processes. For what psi going to? Psi going to psi. Let's see. So we had this. This one, and the one with the legs interchanged. So the convention we'll use is that when you have incoming particles, we're going to change this convention in a second, but when you have incoming particles, you know, I mean, when the momentum is parallel to the arrow, then we call it a psi. So this is an incoming psi, outgoing psi, outgoing psi.
But the vertex allowed from this series psi bar phi psi.
G psi bar psi. Oh, good. You see, the point is that, you know, both psi and psi bar both have creation operators. Remember, we wrote psi as B plus C dagger. Okay, and psi dagger was I'm not writing the exponents. Let me tilde. Psi dagger is B dagger plus C. Okay, so you see, let's say we call particles created by B dagger the particles of type psi. Then psi can annihilate B particles, and it can create C particles. Psi dagger can create B particles and can annihilate C particles. So what happens is, let's say you have BB and BB. So now what happens is, if you have a psi dagger, I mean, so you know, so you see, let's first look at something just like this. You can ask your question in a simpler setup. Let's say you have phi B and you have this, right? This process already is one incoming nucleon, one outgoing nucleon, and one psi. And what happens is this psi destroys this, but on the left you act with this operator, the B dagger operator, right? So do you see? So, you know, do you understand? I mean, this is why we did the Wick contractions first, because the Wick contractions, you know, make this completely clear. So it's not, the vertex doesn't allow one ingoing psi and one outgoing psi bar. The vertex allows one ingoing psi and outgoing psi, or an ingoing psi bar and outgoing psi bar. You can do that also, or you know, both an ingoing psi and an ingoing psi bar, and something and a phi coming out. If you think about charge conservation, you will see it's clear, right? If you have an incoming psi, you can't have an outgoing psi bar, and if you have an incoming psi bar, you can't have an incoming outgoing psi. Is it clear how it happens?
You're telling an outgoing psi bar is an incoming psi.
I'm not saying that. I didn't say that. I just said that, you know, the same vertex can describe, and we'll discuss this a little bit more towards the end of this lecture. I didn't say anything like an ingoing. That doesn't make any sense. How can it be that an ingoing psi is an outgoing psi bar? It can't be, right? Ingoing particle, it's particle which coming from the past, so it can't be an outgoing particle. However, you know, the same vertex can describe an ingoing psi, or it can describe an outgoing psi bar. So the vertex can do the job, you know, the vertex can connect different kinds of possibilities. That doesn't mean that one is the same as the other. They're obviously different possibilities, but the vertex can do all of them.
Vertex has the interaction, right? Psi bar phi. And how can two psi and one phi be?
Because of this. It's an outgoing psi, incoming psi, and phi. So psi, remember, psi has B plus C dagger. psi dagger has B dagger plus C. So this psi dagger, I mean, you can do it other way also, but this psi, goes and annihilates the B, right? Because this is the incoming B, but this psi dagger, to annihilate from the left, you need a creation operator. That's why you can have an incoming psi, outgoing psi, and phi. Is it clear?
This is a valid term in Wix, like in expand.
Yes. I mean, there's not even a Wix expansion here. This is just the first order term. Don't need Wix term. I just want you, it seems to me that you're getting confused about the fact that psi dagger, psi phi seems to suggest that, there's one particle of type psi dagger and one particle of type psi and phi at the vertex. That's not correct, because both psi and psi dagger, contain B plus C dagger, and psi dagger contains B dagger plus C. They're not Hermitian fields. So these are not different particles. It's not like phi 1, phi 2, phi 3. Okay? If it was phi 1, phi 2, phi 3, it would be different. This psi and psi dagger. So this guy can destroy B particles, this guy can create B particles. Yeah.
And
Yeah.
This nucleon, that propagator. When we put the P, the direction of momentum, even if you put it along the arrow or without,
doesn't matter.
The answer wouldn't change.
Yeah, doesn't matter. That P is completely, it's a dummy P, right? You're just going to integrate it over.
So how is it like and that psi bar one, or is it psi?
Well, in the Wick contraction, there's no, you see, as I'm about to say in a second, the direction in which you mark things is it's especially a direction which you mark incoming momenta is completely up to you. Okay. Now you might want to mark, you see, because that particle that sits in the middle is, is not on shell. It's a virtual particle. So, you can indeed, so let's say we do something like this. Right? Okay. Now, in this case, let's say you really wanted to be sure, then, these two are incoming particles. Then it makes sense to mark the P this way, because the momentum is going to run this way and it's going to run out this way. Okay. So if you want to tell a story, you will say you had a nucleon and you mark the momentum this way, because this is the momentum that has positive energy, because this has positive energy, this has positive energy. Of course, you could have marked it this way. It would not make any difference to the computation. But now this P would not have positive energy anymore. It would have negative energy. So that's all you have to okay. So these internal, so you can think of, it's true that you can think of this nucleon going one way with one sign of P as an anti-nucleon going the other way with negative P0, which we'll discuss a little bit towards the end of the lecture. But it's true that this P doesn't make any sense. I mean, not doesn't make any sense, doesn't have any physical effect on how you mark this P. Okay. The question of, is the incoming particle, a nucleon and anti-nucleon, if you really want the intermediate particle, first of all, it's not a very well-defined question, because that particle is a virtual particle, right? So it's important that, the real particles here are just these guys. But if you really wanted to address that, you can try and figure out what the energy of these things are. Okay, and that's something that in this tree level process you can figure out, that if these two have positive energy, then the momentum is flowing this way. Okay. So the story you would like to tell is you have a nucleon, and nucleon rejects another nucleon. I mean, it doesn't, yeah, you might not always be able to figure this out. For instance, let's say I wrote down an interaction which was, okay, let me not say this, it might confuse you. This issue of whether the virtual particle is a nucleon or an anti-nucleon is not always something that can be addressed. Then it might indeed be that, something which is a nucleon which goes forward in time you can think of as an anti-nucleon which goes backward in time, which is related to that. But this is just a problem that goes along with the stories that go with Feynman diagrams, right? So if you just think of what the Wick contraction is and how the diagrams are and what the value is, you never have to worry about this. What you do have to be clear about is what the identity of the external particles is, because that's a physical statement. Okay. What the intermediate particles are doing, and whether it was in particular, especially when you have loops, this is something that can be more confusing. Is the particle that's running in the loop a nucleon, or is it an anti-nucleon? And there isn't actually an unambiguous answer to that. In this case, there is, because you can just see which way the momentum is flowing. But maybe we'll address this again towards the end of this lecture. The time axis is going, no, it's going from right to left. You can make it up the board if you like, but here it's going from right to left. Huh? Here I was thinking of it as going right to left, because you see these two particles are ingoing and these two particles are outgoing. But you can make it do whatever you like. You can draw this diagram like this if you want. There's no rule against that. Or you can draw it like this. That's also allowed. You can make the time axis run from left to right also. You can even make it run top to down. So you can do whatever you like. It's completely a matter of convention. Yeah. I was just trying to follow the convention in the Coleman notes, and roughly along the convention of later is left, that you'd read it from right to left. But it's really up to you. You can do it whatever you like. Are there any questions about any other questions? Okay, excellent. Now, today what I want to do is extract a little bit of physics from what we have done, right? So we did all these calculations of these amplitudes. And today I want to discuss how that can be related to some physics that you might already be familiar with, which is the physics of the Yukawa potential. Okay. And the Yukawa potential is a potential that's created by the exchange of massive particles. And the potential has this form. Okay. So this is the statement that, if you have two particles, they're separated by a distance r, and you can think of them as interacting with this potential, which goes like e to the minus mu r by r, where mu is, sorry, maybe here I should write m, because this is going to be the mass of the particle that's exchanged. Okay, so this is something which is physical. What it tells you is that, if you have a massless particle, then you get long range forces. In the situation where you have massive particles being exchanged, then the force becomes a short range force with a range that's suppressed by 1 over r, 1 over m. Okay, so if you're exchanging a particle of mass m, then that force basically has some range which is controlled by 1 over m. Okay? As opposed to the case where m is equal to 0, where the potential starts looking like 1 over r. Now, the potential is a non-relativistic concept. Okay? We don't really have a notion of a potential in the case of relativity. Okay. Do you know why we don't have a case of a potential in the case of relativity? Huh? Yeah. So the notion of exactly. So if you want to talk about there cannot be a notion of a potential in the case of relativity. It's related to what we discussed in the very first lecture, because the potential can only depend on the last seen distance. Right? So if I give you two particles, I cannot tell you, what is the potential between them. What is because actually that depends on what also the past history of the particles was, or alternately it depends on what the fields are doing. Okay? If you take a static situation, then you can talk of a potential, or you take a non-relativistic situation, then you can talk of a potential. No, there's some notion of a potential, but in general, in quantum field theory, you don't always expect there to be a notion of a potential. Okay? Nevertheless, we are computing something in some relativistic case, and we should have some way of making contact to usual physics and making contact with this non-relativistic. Otherwise, what we are computing would just be something abstract, and we can't just say, well, the potential doesn't make sense in relativity, so we'll never speak of it. Right? We do need to speak of it because after all the potential is something that we measure. And so whatever we have computed relativistically, at least in the non-relativistic limit, should have an interpretation as this potential. Okay, so our answers should have a non-relativistic interpretation. Yeah, and this is an interpretation, and it exists only in the non-relativistic limit, but it's important to understand the physics of what we're doing. Okay, okay, good. So before we go to the answer that we have, I first want to remind you of the problem of non-relativistic scattering. Okay, well, wait. What was the answer we have? Let me also remind you of that. In fact, this was the answer we had for nucleon scattering. It was in fact the diagram we had drawn. So and the other diagram? Okay, so this one looked like K2 minus K4. Doesn't matter. Yeah. That's right. K2 minus K4 square. Yeah. Okay. So this is the answer that we found. Okay, for the amplitude, and then there was a 2 pi to the 4 delta 4. And what is this answer telling us? This is telling us, K1, K2, right? S minus 1, K3, K4. Okay. How do we want to interpret? How do we want to get at the potential? Well, the problem we want to solve is, let us say there was some potential which was V of R between the two particles, which in the non-relativistic setting makes sense. What would then have been, this problem we could have solved also in the non-relativistic setting, where we could have taken two incoming particles, two outgoing particles, and they interact with some potential between them, and we could solve for how they scatter off each other. And what we want to say is, we want to match this answer that we have, okay, for S minus 1 in this limit with the answer that we would get in the non-relativistic quantum mechanical case. Okay, and then using that we can determine what the V should be. So is the objective clear? We have an answer for some quantity. This quantity is something that makes physical sense even in the case of non-relativistic scattering, because it's a physical quantity. It's saying I scattered two things with K1 and K2. What's the amplitude they come out with K3 and K4? Okay, good. So there are many parts to this answer. There is the delta function, which is energy momentum conserving. There is, there are these different terms and so on. And so let's see if we can match all of them. Yeah. So what I want to do actually is address the non-relativistic problem, because I'm assuming that you've all seen some scattering theory in the case of in non-relativistic quantum mechanics. However, there are some subtleties that are associated with this problem, because it's actually a two-body problem. It's not a one-body problem. And so, we have to first convert it to some reduced one-body problem. And then there are some additional subtleties that are associated with Bose statistics that, at least in the conventional description of scattering, you might not have seen. And so I'm going to now spend some time discussing that. Yeah. So for some time I'm just going to do non-relativistic quantum mechanics. Okay. So I'm going to go back to thinking of two particles which are scattering off each other. Okay. And that's a okay framework to discuss this. We have two nucleons. In the end also we have two nucleons. Okay. So the degrees of freedom are described by a wave function which is psi x1 x2. Okay. And it's a function of time. Okay. And it obeys, it obeys psi by dt. I here, and then let me write minus b1 squared minus b2 squared and back to n. Okay, so there is some, some equation which this wave function obeys. This is the time dependent Schrodinger equation, and we want to solve this as you go from forward to back. Okay, okay, good. Now there's an assumption we need to make about the potential, which is this is some general potential which depends on x1 and x2, but we want to assume that the potential is translationally invariant. That's an important assumption that also went in there, right? The field theory we were doing was translationally invariant. So the potential can't depend on x1 and x2 separately. It can only depend on x1 minus x2. These, by the way, are vectors. Okay. Okay. So now, there are two degrees of freedom here, which are x1, x2. Okay? But you see that the potential only depends on one particular combination. So in fact, you can write this wave function as some wave function Now, this is not the most general solution to this. In general, you could try and take linear combinations of this kind of thing. But the simplest kind of solution you have to this problem is one where you don't have entanglement between this side and this side. And the wave function you can just write as a product of something that depends on the center of mass degree of freedom and this degree of freedom. Okay, so this is this. Okay. Okay, and of course, it's important in this. Let me try and make. In some of what I'm going to do, I'm going to work today in the units where 2 is equal to 1. Okay, as I threatened to do earlier. So you can check some of these things carefully because what we want to get in the end is the form of the potential. There'll be some constants in front that I'll try to get right, but I don't promise. Okay, so you should check. Okay, and I think that's because we didn't put a half in. Sorry. It's because we didn't put a half in defining these variables. Okay. Okay. So in this situation, this term, the kinetic term, also breaks up into a kinetic term that depends only on x1 minus x2, and a kinetic term that depends only on x1 plus x2. Okay. So you can use this to read off, what equations, how when you separate variables, and this one obeys, let's call this COM, let's call this C, and let's call this D. Okay. So the equation of motion for the center of mass is this, okay, and then there's an equation of motion for the difference Okay, is it clear how we have separated the variables? Yeah. So what I said is that there's a wave function, there's a time-dependent Schrodinger equation, but in fact there are two separate degrees of freedom. One degree of freedom is the center of mass degree of freedom, and the center of mass degree of freedom, decouples in this setup from the behavior of this difference degree of freedom. Okay, and the gradient, the kinetic term also separates, so you get psi c satisfies this, psi d satisfies this. Okay, and you can check that if indeed psi c and psi d satisfy this, then the whole thing will satisfy this equation. Okay, and that's because this derivative you can write as a derivative on time acting on this plus a derivative of time acting on this. Okay, and if the derivative on time acting on this absorbs one part of the kinetic term, and the derivative of time acting on this absorbs the other part of the kinetic term and the potential term. Okay, so is this manipulation clear, this separation of variables? Okay, good. Now we also want to work in momentum space because our answers there were in momentum space, the answer there was not in position space. Okay. So we want to relate how the momentum space that we have for x1 and x2 relates now to the momentum space that we have for psi and for this psi d and for psi c. Okay. So notice the following fact, that if I look at e to the I k1 x1 plus k2 x2, okay, this looks like e to the I k1 plus k2. Sorry, these are all three vectors, which will be important in a minute. Okay. So if you take, if you put particle 1, and this I think follows, because you get k1 x1 plus k2 x2. Okay. Here also you get k1 x1 plus k2 x2 because the minus sign cancels. There are also some cross terms. You get a k1 x2, okay, but from here you get a minus k1 x2. You get a k2 x1, okay, but from here you get a minus k2 x1. So the cross terms cancel, and you're left back with this. Okay. What this tells you is that the momentum that is associated with this degree of freedom, okay, is k1 plus k2, and the momentum that's associated with this degree of freedom is k1 minus k2. Okay. So the momentum by 2. Okay. Okay. However, notice that let's say I wanted a basis of momentum eigenstates for this set of particles. Okay. Is this a valid set of momentum eigenstates? Can I expand the wave functions in this set of momentum eigenstates? The answer must be no, since I'm asking you, but why is it no? Yeah, okay, these are free, but free doesn't stop, free is fine. You can still expand, you can, the answer might not, momentum eigenstates might not be energy eigenstates, but there's something else that's wrong with this. Translationally invariant, no, I mean, momentum eigenstates are not quite translationally invariant. They transform in a phase under translation. If you look at that answer, actually you'll already, if you look at what we're discussing there, you might give you a hint to what is wrong with this. There's some physics also that goes along with that answer, which is actually an important part of the physics here. And the momentum conservation is coming in the scattering amplitude, but there's something else. Okay, you see these are identical particles. So there's a constraint I have to impose on them, which is that psi x1 x2 t is equal to psi x2 x1 t. That's why we got those two diagrams above. Okay, so I can't just expand things, in this basis where I have k1 x1 plus k2 x2. Okay. Alternately, let's say I have written the wave function as a product of this and of this, then this part is symmetric under the exchange of x1 x2 by construction. This part is not symmetric under the exchange of x1 x2. Okay. So must be written as a sum of, or as an integral of ek times cos of k dot x1 minus x2. Okay. So you can think of it, not as a d3k and so on. And this ak is just a coefficient. I'm just talking about a Fourier expansion. I'm not there are no creation annihilation operators here. The main point is that the basis of in which you expand x1 minus x2 is not a basis of plane wave exponentials, because plane wave exponentials are in general not allowed by symmetry. So I have to choose something that is symmetric under the exchange of x1 x2. I can't choose sine, I have to choose cos. Okay, sine would be antisymmetric, cos would be symmetric. Okay, so it's important that when you think of saying that the difference is in some eigenstate of momentum, the associated wave function is cos. It's not e to the ik dot x. Okay, and this is important because if you don't keep track of this, you'll find that the answer that you have doesn't match the answer that we get upstairs. Okay, so field theory is clever. Field theory is clever because field theory automatically keeps track of Bose statistics. In non-valid, that answer that we got, we just got it, right? We didn't have to do anything. I mean, we drew those two diagrams, but before that we did the Wick contractions, and we just looked at all possible Wick contractions and we got the answer that we got, right? We didn't have to say, k1 k2 was the same as k2 k1 or keep track of things. In non-relativistic quantum mechanics, you have to keep track of Bose statistics by hand, okay? Because you are allowed to have particles which are distinguishable. Okay? And in fact, as I said at the beginning, one of the interesting physics things that comes out of field theory is this, that field theory automatically tells you that particles which are created by one field are identical particles. So this is in fact something which is not always emphasized in textbooks, but is an important aspect of the answer that we have. That in the field theory answer, we automatically got an answer that was consistent with Bose statistics, whereas in non-relativistic quantum mechanics, you see, we have to impose the constraint by hand. And by hand say that we are only allowed this set of wave functions. Okay, there's nothing in the mathematical formalism that tells you that this is not allowed. And mathematically you could work with this. Okay? But if you want an answer that matches with field theory, you'll have to impose this constraint by hand. Okay. Okay, good. Okay, good. So now let's work out the scattering amplitude, right? So what is the scattering amplitude? We start with some k1, k2. Okay, we start with some initial state which is k1, k2. Of course, as we said, it's actually e to the I k1 x1 plus k2 x2 plus e to the I k2 x1 plus k1 x2. Okay, so it has a sum of those two terms, which you can write as this k1 plus k2 into something plus the difference plus into cos of the difference. Okay, okay, good. Now let's try and understand what the non-relativistic answer will be for the scattering process. Okay, first let's consider the scattering of okay. Now, by the way, we converted the Schrodinger equation, into two separated equations, right? So we can consider the scattering process separately, right? And the amplitude we get will just be the product of the two amplitudes. Okay, so let's consider COM scattering. So the C1 scattering is just free particle scattering. You see why? It's because the center of mass, that equation that we have on top is a free particle equation. Right? So what amplitude does it contribute? If you start with free particle, you start with momentum k1, where could it go to? It has to go back into k1, right? Okay. So in this case, it's going to give you a 2 pi cubed into a delta cubed, okay, of k3 plus k4 minus a k1 plus k2. Actually, this is where I'm using the units 2 is equal to 1, okay, because we said the momentum here was k3 plus k4 by 2, which will give you some factor of 2 in the delta function. I could try to keep track of it, but I'll almost certainly not succeed. Okay, so I'm going to write the answer this way. If you want to be very careful, you can put the factor of 2 and keep track of overall factors of 2. Okay, okay, let me try. Although I think I won't succeed. Okay, I'm not even sure if I'll get the answer right if you keep track. Okay, but the important fact is that you get this. Okay, the physics part is you get this. You see why it's a delta cubed and not a delta 4? Because it's non-relativistic scattering, and non-relativistic scattering, there's one particle, right? The physical interpretation of that is there's one particle. You started off with momentum k1 plus k2 by 2. It ends up with momentum k3 plus k4 by 2, and the amplitude is just this delta cube. There's no delta 4 or anything that's going to happen. There's a 2 pi cubed, and that's it. Okay, this is the amplitude. Okay. Okay. Then there is this difference scattering. Okay, I don't know if you guys remember or are familiar with the general formula for the difference scattering, but the general non-relativistic formula is that k s minus 1 k prime, okay, is equal to minus I by delta E minus E prime minus 1. This is probably a formula just for S. Okay. Okay. So where this is some Green's function, okay, that you have to keep track of, but and these are the external states, and in non-relativistic scattering you do get a delta function, okay, and you get a delta. Actually, maybe I should write this as S minus 1 is this minus 1. Yeah, you do get a delta function, and the delta function that you get is a delta function that conserves energy. When you have scattering of a potential of a non-relativistic particle, and the potential is given by V, then the initial energy, the initial momentum might not be the same as the final momentum, because the potential causes scattering. So you can scatter off a potential and go somewhere else. However, the initial energy is the same as the final energy. Okay, this is a general fact of scattering in non-relativistic potentials. So you do get a delta function if you do this carefully. Are you all familiar with this formula? You're familiar with some version of it. I'm not sure how carefully this is always done, but if you want, go look at Sakurai, and it'll explain this. So there is a delta function that you get in the S matrix that corresponds to scattering with with energy conservation, and then you get some other bunch of terms, okay, which you have to evaluate between the momentum eigenstates, and that's what gives you the scattering amplitude. Okay. Okay, good. Now the leading term that we have is actually pretty simple, and it just corresponds to, let's call this k initial and k final. Okay, so the lead, let me see if I get my factors. Yeah. Okay, so I don't think I'm going to get my factor. To leading order, this guy is just minus I 2 pi delta E minus E prime, okay, into V of x into e to the I ki minus kf C vector dot x. Okay. This is what it looks like in general in non-relativistic scattering. Okay. However, so in our case, k initial would be k1 minus k2 by 2, k final would be k1 plus k2 by 2. However, here there's a difference. Okay. And what's the difference? The difference is the fact that we have both statistics. Okay. So you also have to consider the term where ki goes to minus ki. You also have to consider a term where kf goes to minus kf. Okay, but there are 4 possibilities. And so in general, there's also this term. In our case, let me erase this part. Okay, let me erase it and write it clearly. I want to keep this expression. How do I do that? Let me write this on top. This expression I want to keep. We get minus I 2 pi delta E minus E prime, okay, integral V of x into e to the I ki. This is initial minus final, okay, ki minus kfx. This is what it would have been without Bose statistics. With Bose statistics, it's this plus e to the I ki plus kf dot x. Okay. Here I'm not really not being careful about the normalization of the wave functions. It will affect what you get for the 2 pi. Okay, but I'm going to give up trying. Okay. So you see, the important fact is that you get one term. This is the term you've studied in your usual non-relativistic quantum mechanics. You start with momentum ki. You end up with momentum kf. And what is the answer that you get? Where it looks like the Fourier transform of v of x with the momentum ki dot kf. Okay, these are 3 momenta. Okay. However, due to Bose statistics, and this is an effect that you might or might not have seen, there is an additional term that you get that looks like ki plus kf. Do you see why you get that term? Because in fact, the momentum eigenstates that you have in this formula, you should put k is equal to cos of kix. So you'll get cos of kix into cos of kfx. Okay. And when you do that, you will find one term which will look like ki minus kf and another term which will look like ki plus kf. Okay. There are also terms which will look like minus ki minus kf and minus ki plus kf, but they'll give us the same answer. Okay. They'll give us the same answer because this potential that we have is symmetric under x goes to minus x. Okay. Okay. But the important part is that you get this and that. Do you see this? Yeah. Okay. So this is the answer that we will get, if you were to compute the case with non-relativistic scattering. Now, what is ki for us? Okay. So okay. Let's also do it's already looking a little bit like what we have there. Remember, ki is k1 plus k2 by 2. Kf is k1 minus k2 by 2 is k3 minus k4 by 2. Okay. So what we are calling ki here is k1 minus k2 by 2, and what we are calling kf is k3 minus k4 by 2. Okay. Okay. Good. Now let's to do this a little bit more. Let's also parse this integral a little bit. Okay. So let's just do this integral. Let's try and do v of x times e to the I q dot x d3x. I just want to do this Fourier integral. So this will give you this Fourier integral will give you d of x. So let's imagine that the potential we have is spherically symmetric, which in this case makes sense because there's nothing that's breaking spherical symmetry either. So I just want to explain what happens here so that we can match correctly. Yeah. So this looks like V of r I q r cos theta d of cos theta into r squared dr. Okay. And this looks like that's because you can always choose the axis of q and x to be aligned to each other. And this looks like 2 pi times integral 4 pi times integral v of r times r by q times sine qr. Okay. And the way this comes about is you do the integral of cos theta of this, so you get e to the iqr minus e to the minus iqr divided by iqr. Okay. One of the factors of r cancels the r square here, so it converts the r square into an r. The q sits behind, and the e to the iqr minus e to the minus iqr by twice I becomes sine qr. So you get this. Okay. Okay, good. So now we just have, almost everything is working out correctly. Let's just also try and match. So, we have to find some, so, the expression that we have looks like v of x times this, okay? So we have to find, some v of r so that when you integrate it with ki minus kf and ki plus kf, where ki is that, okay, it will match and give you that expression that we have there, okay? However, there's another part, and we'll see what that thing is in a minute. There's another part of that expression which is this 2 pi 4 which is hidden, okay, and that's a delta function of 4 variables. Okay? It's k1 plus k2 plus k3 plus k4. Okay? Now what we have here is a slightly different combination. We have 4 delta functions here as well, but they're slightly different delta functions, right? Because they look like k3 plus k4, okay, minus k1 plus k2, 3 delta functions, and then you have this e minus e prime. Okay? What is e and what is e prime? So what is e minus e prime? Looks like k1 minus k2 squared, okay, into up to a factor 1 by 4, but doesn't matter, 1 by 4m minus k3 minus k4 squared, maybe by 8m. Okay. Okay. Do you see this? Okay. Now you might think, this looks pretty different from the answer that we have up there. Okay. However, it doesn't look very different because in fact, so the delta function we have is a delta of this. There's an 8m which will give you an 8m up front, okay, which I'm again going to drop, and we have a delta cubed of k1 plus k2 minus k3 minus k4. What you have to compare it with is a delta function of 4 things. Okay, is that 4 delta function there. Okay? So what you need to do is compare this guy with the delta function that looks like delta of square root of k1 squared plus m squared plus square root of k2 squared plus m squared minus square root of k3 squared plus m squared minus square root of k4 squared plus m squared. Right, you see that? So you have to compare this delta function with this delta function. But remember, we don't expect them to match in general. we only expect on the other side we have some 2 pi to the 4, and then there's the same delta cube. We don't expect these delta functions to match in general, but only match in the low energy limit, right? When these momenta are small compared to the mass. When you do that, you should expand this delta function as this term looks like m squared, okay, plus k1 squared by twice m plus m squared plus k2 squared, m plus k2 squared by twice m minus m minus k3 squared by twice m minus m minus k4 squared by twice m. Yeah. Okay, the m's are all going to cancel. Okay, we still have something that looks different. Here you have k1 minus k2 square minus k3 minus k4 squared. But remember, there's an additional delta function that's telling you k1 plus k3 is equal to k3 is equal to k3 plus k4. Okay, so in that situation, you can freely add to this k1 plus k2 on this side squared and subtract from it k3 plus k4 squared, because k1 plus k2 is equal to k3 plus k4. You see that? And then this indeed becomes k1 square plus k2 squared, and this indeed becomes k3 square plus k4 squared. Okay, so the delta functions actually do match. In this case, this is just equal to k1 minus k2 squared plus k1 plus k2 squared, just using this identity, minus k3 minus k4 squared minus k3 plus k4 squared, and then using the fact that there's an additional delta function that sets k1 plus k2 equal to k3 plus k4. Okay, so up to another factor of half, which we're going to drop, you see k1, this squared, this energy momentum conserving delta function is in fact the same as the one we get in the non-relativistic case. Okay. Okay, good. Okay, so now we only have to know one more identity. Okay. That's right, because we are trying to match with a non-relativistic answer. So what sense would it make to try and match away from low energy, right? Only makes sense to try and match the low energy term. So it's important actually that the answer in general of the non-relativistic case is not the same as the answer of the relativistic case. How can it be? It's only that in the low energy limit, the answer of the non-relativistic case turns out to be the answer of the relativistic case. Yeah. Okay, good. Now, okay, good. Now, one more thing. I'm sorry, we have to do lots of manipulations to make this work, but all these manipulations have a little bit of physics. The answer that we have there looks like we still have to make the two boards match, but let's try. Okay. The answer that we have here looks like an answer where you have k1 minus k4 squared, and that looks a little bit like what you might get from the right potential if you put in the right kind of Qs, except that whatever you get there can only depend on the three vectors and not on 4 vectors. Whereas here you have something that looks like it depends on 4 vectors. Okay. However, this answer that you have is a Lorentz invariant answer. So we can go to to evaluate the answer. This is actually something which we don't. It's not a choice. It's just an this answer doesn't depend on which frame you evaluate it in. Okay. So let me choose to I could make the answer look more complicated in some other frame, but let me choose to go to the center of mass frame. That will just help things in that there are some delta functions and so on that I won't need to use to get the answer that I want. In the center of mass frame, what do we have? In the center of mass frame, we have K1 is equal to minus K2, right? Because the incoming particles are cancelling, and we have K3 is equal to minus K4. What that tells you actually is that the energies of all of these particles, okay, because so what that tells you is that K10 is equal to K20, okay, K30 is equal to K40, okay, and so all these energies you don't need to. One second, let me just make sure I'm not saying something wrong. Good. Yeah, that's right. So I think this is fine. Remember also that mod of K1 plus mod of K2 or K10 plus K20 is equal to K30 plus K40. Okay, but K10 and K20 are the same because K13 vector is the same as K23 vector, and we have a Marshall relation. So that tells you actually that K10 is equal to K20 is equal to K30 is equal to K40 in this frame. All these energies are the same in this frame, okay? And they are half of the total energy, and that's because all the particles have the same mass. Okay? Good. So therefore, in this frame, I can write this answer as minus Ig squared into 1 by K13 vector minus K43 vector, okay, squared plus m squared, because there is no difference in the energies, but the minus sign has also gone, okay, plus okay, just that operative part. Okay, good. Now this is in fact the same as what we had upstairs. If we identify this with, I'm sorry, this has become a bit of a mess. We had, remember there's a Ki which was K1 minus K2 and Kf which was K3 minus K4. You see there on top Ki and Kf. Okay. In the center of mass frame, okay, this is in the COM frame. In the COM frame, which is where we are matching this, Ki is in fact just equal to twice K1. Okay, and Kf is just equal to twice K3. Okay, or you can think of it as equal to minus twice K4. So Ki minus Kf. Did I get my sign wrong? 1 second. Sorry, I got my sign wrong. 1 second. Kf is K3 minus K4 and K1 is no, it's okay, no? Why? What? No, it's okay. This K1 minus K4 and K2 minus K4. It's okay. There's no problem. Why is there a problem here? That's how the answer was. Remember, the answer was K1 minus K4 and K2 minus K4. I mean, there are two terms here. One looks like K1 minus K4 and K1 minus K3 or K2 minus K4. In this frame, it looks like K1 minus K4 and K2 minus K4. Okay. In fact, these things are, you see, K2 is just the same as minus K1. Okay. So Ki minus Kf is just equal to twice of K1 plus K4. Okay, that's one term that you have here, which is K. You can think of this as K1 plus K4 because K2 is minus K1. Okay, and Ki minus Ki plus Kf is just equal to twice of K1 minus K4. Maybe we had some factors of 2 also. So in fact, even the 2 is not there. Yeah. Maybe this is just K1, K2, K2 because we anyway had factors of 2. Yeah. So you see, this is matching very nicely with what we have here. Okay, this one of them is Ki minus Kf. That's this one, and the other one is Ki plus. Which one is Ki plus Kf? This one is Ki plus Kf. Yeah, sorry. This I can think of as minus K2 plus K4. This one is Ki minus Kf squared, and this one is Ki plus Kf squared. You see that? Yeah. Okay, good. So this answer in the COM frame looks like minus Ig squared into 1 by Ki 3 vector minus Kf. I'm now using this notation squared plus m squared. Okay. Plus 1 by Ki plus Kf 3 vector squared plus m squared. Okay, all in the COM frame. Huh? No, plus m squared because earlier you had minus m squared. Okay, but you remember that the convention we have is that the time lag comes with a positive sign and the space lag comes with a negative sign. Okay? So the time lag part just vanished because the time lag part was giving you 0 in this frame. So you have minus of K1 plus minus K3 vector squared, and that's the same sign as the m squared. However, as a result, this might become a plus Ig squared. Okay, so it's actually the same. Okay, so this is almost done, right? Because we're almost done. All we now need is to match V of R. You know, we already have this kind of expression, which is Ki minus Kf plus Ki plus Kf. If we can find a V of R, so that V of R times sine of QR gives you 1 by Q square plus M square, we are done. Okay. I know this has been a bit of a mess, so I'll just recap the whole thing because it's been a little, we've been trying to match things from both sides. Okay, now we have the following identity. Which is that e to the mr by r into sine qr by q dr, okay, is equal to 1 by q squared plus m squared. Okay, so you see that if you take v of r to be e to the mr by r, then this answer will become up to various factors will become, let me try and keep track of factors to the extent I can, 4 pi and maybe 8 pi squared minus I delta phi minus E prime 1 by Ki minus Kf the whole squared plus m squared plus 1 by Ki minus Kf the whole squared plus m squared. Okay. So if you take V to be this potential, okay, I'm trying to keep track of factors as best as I can. I don't know if I've kept track of them very well. Then this answer becomes this. V is e to the m r by r. What?
This formula which you have written, right? V of r into r by q.
No. There's an r here in the formula. There should be an r in the formula. R dr. What it should be minus m. Thank you. Yes. Okay. Okay, this is just some identity. You can go look it up or do it in Mathematica. We can actually, this identity is not hard to derive. Even we can derive it. See, the r just cancels, right? So it's just e to the m r into sine qr. So it's e to the minus m plus iq and e to the minus m minus iq. So you get 1 by m plus iq, 1 by m minus iq. It gives you q by q square plus m square. So even I can do this integral. Yeah. Okay, good. So you see that this expression, if you take v to be this, gives you this. Okay, good. Now this is correct, right? Because that tells you that the full non-relativistic answer so the full NRQM amplitude maybe I should put a V naught here just to make the potential go like V naught into something. So the full NRQM amplitude is proportional to some V naught times delta of E minus E prime delta cubed of K minus K prime K1 plus K2 one second, delta of K1 minus K2 squared minus K3 minus K4 squared K1 plus K2 minus K3 minus K4. I'm just summarizing everything because it might have been a little confusing into 1 by actually the answer looked like 1 by into 1 by K1 minus K4 squared plus m squared plus 1 by K1 plus K4 squared plus m squared in the COM frame. Okay. Actually, the full non-relativistic amplitude looks like something slightly different. It looks like K1 minus K2 minus K, minus K3 minus K4 by 2, and the other one Ki minus Kf. But in the center of mass frame, it looks like this. Okay. And the full relativistic amplitude, I've put a proportionality sign because by now we've dropped a lot of factors inside this delta function, and I've given a full QFT amplitude